Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Let your body sink into whatever surface is supporting you. There's nothing urgent waiting for you here, just a slow, peaceful journey through one of humanity's most beautiful achievements. Where in the world are you watching from tonight? A quiet bedroom where the day is finally winding down? A cozy corner where you can finally let your mind rest? Wherever you are, you're exactly where you need to be. Tonight we're going to explore the Voyager mission, two spacecraft that left Earth nearly 50 years ago and are still travelling, still speaking to us from the edge of everything we know. We'll discover how they were built, the worlds they visited, the data they sent home, and what it means that they're still out there, moving farther away with each second that passes. It's a journey that spans not just our solar system, but touches on questions about who we are, what we hope for, and what we leave behind when we reach into the darkness beyond our small blue world. But don't worry, this isn't going to be a dramatic countdown of crises and near disasters. Instead, we'll move slowly and carefully through the missions, taking our time with each world they visited, each discovery they made, each quiet triumph of engineering and human persistence. By the end, I think you'll find something deeply peaceful in knowing these two small machines are still out there, carrying our message to stars we'll never reach. If you enjoy these calm explorations of space and science, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here. Your presence in this community of quiet learners means everything, so settle in, let your shoulders drop, take a slow breath, and another. And let's begin our slow drift through the story of Voyager, humanity's farthest reach into the cosmos. There's nowhere you need to be right now, nothing you need to do. Just listen and let the story unfold. The spacecraft are still travelling, and tonight, so are we. Before Voyager ever left Earth, before the rockets were fueled or the final checks completed, a small group of scientists and artists gathered to answer an impossible question. If we could send a message to alien civilizations, what would we say? What would we choose to represent all of humanity, all of Earth, in a package that could fit on a 12-inch copper disc? The result was the Golden Record, and it remains one of the most thoughtful, hopeful gestures our species has ever made. Picture it, a gold-plated copper disc, grooved like an old phonograph record, sealed in an aluminum case with instructions etched on the cover. The instructions are in what Carl Sagan and his team hoped would be a universal language, using the physics of hydrogen atoms and simple mathematical symbols to explain how to play the record, how fast to spin it, how to decode the images it contains. On that record they play sounds from Earth. A baby crying, wind and rain and thunder, surf breaking on a beach, animal calls, dozens of them, from whales singing in the deep ocean to wolves howling under stars, footsteps, heartbeats, a kiss. The sound of a mother and child talking. They recorded greetings in 55 languages, from ancient Sumerian to modern Mandarin, each speaker offering a simple message of peace and goodwill. "Hello from the children of planet Earth," one greeting says in English. In Welsh, "Good health to you now and forever." In Urdu, "Peace on you. We the inhabitants of this earth send our greetings to you." There's music too, 90 minutes of it, carefully chosen to represent the breadth of human musical expression. Bach and Beethoven, yes, but also Blind Willie Johnson's blues, a Navajo night chant, a Peruvian wedding song, Japanese shakuhachi flute, pygmy girls singing in Zaire. Chuck Berry's quote 3 made the cut, a bit of rock and roll heading toward the stars. Each piece was selected not just for its beauty, but for what it revealed about human creativity, human joy, human longing. And there are images, 115 of them, encoded as audio signals that can be converted back into pictures. Photographs of Earth from space, showing the planet as a whole, blue and white and beautiful. Images of human anatomy, of people from different cultures, of our cities and our wild places, pictures of DNA molecules and mathematical equations, of animals and insects, of a sunset and a snowflake, a supermarket, a traffic jam, a woman nursing a baby, an old man with a walking stick. They tried to show both our knowledge and our nature, our technology and our tenderness. The team worked urgently because the launch window was approaching and couldn't be delayed. They had months to do what really deserved years. Yet what they created feels neither rushed nor incomplete. It feels instead like a love letter. Not naive, not ignoring the violence and pain that are also part of human experience, but choosing to emphasize what we hope for rather than what we fear. The record isn't meant to be comprehensive. It's meant to say, this is some of who we are. This is some of what we've made and discovered. This is some of what we love. The golden record will outlast everything else we've built. Long after the spacecraft carrying it have gone silent, long after Earth itself might be unrecognizable, those records will still exist, drifting between stars, carrying their message. In 400 million years, Voyager 1 will pass within about 1.5 light years of a star called Gliese 445. Voyager 2 will come within a similar distance of Sirius in about 300,000 years. By then, the sun will have changed, the continents will have shifted, species will have risen and fallen, but the record will remain, playing its small symphony of Earth to the silence. And that's where our story begins, with that record and the hope it represents. Attached to 2 spacecraft about to embark on a journey longer than any mission ever attempted. Which brings us naturally to the question, how do you launch something into forever? The summer of 1977 was humid in Florida, the air thick with moisture and anticipation. At Cape Canaveral, 2 identical spacecraft waited for their moment, built with exquisite care, tested and retested, packed with more instruments than any previous probe. They were called Voyager, and despite their identical construction, they would take different paths and see different wonders. Voyager 2 actually launched first, on August 20th, 1977, aboard a Titan Centaur rocket that pushed it away from Earth with a roar that shook the ground for miles. But it's the second launch, Voyager 1 on September 5th, that captures something essential about these missions. By then, the teams knew what was at stake. The launch window existed because of an alignment of the outer planets that happens only once every 175 years. Jupiter, Saturn, Uranus and Neptune were arranged in such a way that a spacecraft could use the gravity of each planet to slingshot toward the next, gaining speed with each encounter, making a grand tour of the outer solar system possible with the technology of the day. Miss this window, and no one alive would see another chance. The spacecraft themselves were small, really. Each weighed about 825 kilograms, about the mass of a small car. But every gram of that weight was purposeful. The scientific instruments were mounted on a scan platform that could point in different directions, taking photographs and measurements as the spacecraft flew past their targets. There were cameras, obviously, but also magnetometers to measure magnetic fields, plasma detectors to taste the solar wind, cosmic ray detectors, infrared and ultraviolet spectrometers to analyse the chemistry of planetary atmospheres. The most distinctive feature was the high-gain antenna, a dish 3.7 metres across that would serve as the spacecraft's link to Earth. Next to it, a long boom extended out, holding the magnetometer away from the spacecraft's own magnetic fields. Another boom carried the radioisotope thermoelectric generators, 3 of them, containing plutonium-238 that would decay slowly, producing heat that could be converted to electricity. These RTGs would provide power for decades, long after solar panels would have become useless in the dim light of the outer solar system. Launch day was perfect. Clear skies, light winds. All systems showing green. At 7:29 in the morning, Voyager 1 lifted off, climbing on a pillar of flame, pushing through the thick Florida air and into the thinner atmosphere above. The first stage burned for a few minutes, then fell away. The second stage fired, pushing the spacecraft faster. Then the Centaur upper stage ignited, burning for 5 minutes to push Voyager toward its cruising speed. Finally, a small solid rocket motor gave the final kick, sending Voyager 1 on a trajectory that would carry it beyond Earth's gravity toward Jupiter. The engineers watched their telemetry screens, seeing the numbers that represented years of work now translated into motion, into distance growing second by second. Everything worked. Every system came online as planned. The spacecraft oriented itself using the sun and bright stars as reference points, then turned its instruments toward Earth one last time before beginning its outward journey. What must it have felt like for the people who built these spacecraft to watch them disappear into the sky? They had touched these machines with their own hands, had solved thousands of problems, had tested and retested every component. They knew that once Voyager left Earth, they could never touch it again, never repair it, never fix an unforeseen problem except by sending radio commands that would take hours to arrive. The spacecraft were on their own, carrying instruments worth hundreds of millions of dollars, representing not just American engineering but a collective human desire to explore, to know, to reach beyond what seems reachable. And yet there must have been joy mixed with the anxiety. Because the launches worked. Both spacecraft entered their planned trajectories. Both began their long coast toward Jupiter, which was still more than a year away. Both were healthy, transmitting data, responding to commands. The grand tour had begun, and everything humanity hoped to learn from the outer planets was now possible. The question was simply, what would they find? That question would start being answered as the spacecraft approached their first target, the largest planet in our solar system, a world so massive that all the other planets combined would fit inside it with room to spare. 16 months after launch, in March of 1979, Voyager 1 approached Jupiter. The planet had been growing in the spacecraft's cameras for weeks, transforming from a bright point of light to a disk, then to a world of such complexity and beauty that even the scientists who had studied Jupiter for years found themselves surprised. Jupiter is vast beyond easy comprehension. Its diameter is 11 times Earth's. You could fit 1,300 Earths inside Jupiter's volume. It spins faster than any other planet, completing one rotation in just under 10 hours, which creates tremendous forces, winds that howl at hundreds of kilometers per hour, weather systems larger than our entire world. The Great Red Spot, a storm that has been raging for at least 350 years, is 2 or 3 times the diameter of Earth. Imagine a hurricane that has been spinning for centuries, that shows no sign of slowing down, and you begin to grasp the scale of Jupiter's atmosphere. Voyager 1 flew through the Jovian system for 4 months, taking thousands of photographs, measuring magnetic fields, tasting charged particles, studying the complex interaction between Jupiter and its retinue of moons. What it found was not just a planet but an entire system, a miniature solar system with Jupiter as the sun and dozens of moons orbiting in complex patterns. The closest approach came on March 5th, when Voyager 1 passed within 280,000 kilometers of Jupiter's cloud tops. At that distance, the instruments could resolve details as small as a few kilometers across. The images that came back were revelations. Jupiter's atmosphere isn't just bands of colour, it's a churning, evolving system of storms and jets, eddies and currents, structures that form and dissolve on timescales from hours to centuries. The colours come from chemistry, from sulfur and phosphorus and organic compounds created by lightning and solar radiation, tinting the clouds in shades of brown and orange and red and white. But perhaps the greatest surprises came from the moons. Io, the innermost of Jupiter's 4 large moons, turned out to be the most volcanically active body in the entire solar system. Voyager 1 caught volcanic eruptions in progress, plumes of sulfur dioxide gas shooting hundreds of kilometers above Io's surface. These weren't ancient, extinct volcanoes. They were happening now, driven by the immense tidal forces that Jupiter's gravity exerts on Io, kneading the moon's interior like bread dough, generating enough heat to melt rock and drive constant, violent eruptions. Europa, the next moon out, showed a surface of fractured ice, crisscrossed with lines and cracks, but with almost no impact craters. The lack of craters meant the surface was young, constantly renewed. The cracks suggested something moving beneath the ice. Scientists began to suspect what would later be confirmed. Europa has a global ocean of liquid water beneath its frozen shell, kept liquid by the same tidal heating that makes Io volcanic. That ocean might be 100 kilometers deep, containing more water than all of Earth's oceans combined, and it might, possibly, harbour life. Ganymede and Callisto, the outer two large moons, showed their own distinct characters. Ganymede turned out to be the largest moon in the entire solar system, bigger than the planet Mercury, with its own magnetic field. Callisto's surface was ancient, battered by billions of years of impacts, a record of the solar system's violent youth preserved in ice. Voyager 2 arrived at Jupiter 4 months after its twin in July of 1979 and confirmed what Voyager 1 had found while adding its own discoveries. Together, the two spacecraft revolutionized our understanding of Jupiter, transforming it from a distant gas giant studied through telescopes into a complex, dynamic world with its own weather, its own magnetic environment, its own family of diverse and fascinating moons. But they couldn't linger. Their trajectories had been carefully calculated to use Jupiter's gravity to fling them onward, towards Saturn, gaining speed from the encounter. As they departed, Jupiter shrank behind them, returning to a bright point of light. But ahead lay another giant, one with its own unique beauty, its own mysteries waiting. Imagine, if you will, a planet so beautiful that even in blurry telescope images from Earth, it takes your breath away. Saturn has been known since ancient times, but it wasn't until Galileo turned his primitive telescope toward it in 1610 that anyone noticed it looked strange, with what appeared to be handles or companions on either side. It took decades for astronomers to realize what they were seeing. Rings, impossibly thin bands of material circling the planet's equator, visible even from over 1 billion kilometers away. Voyager 1 reached Saturn in November of 1980 after a journey of 3 years. The encounter was planned down to the minute, with the spacecraft's trajectory carefully chosen to provide both good views of Saturn and its rings, and a close flyby of Titan, Saturn's largest moon. As Voyager approached, the rings resolved from a few bright bands into a structure of stunning complexity. What Voyager found was not 3 or 4 rings, as Earth-based telescopes had suggested, but thousands of individual ringlets, each orbiting Saturn at its own speed, separated by gaps and divisions, woven into braids and spirals by the gravitational influence of Saturn's many moons. The rings turned out to be made mostly of water ice, chunks ranging in size from dust grains to house-sized boulders, each one an independent moon orbiting Saturn, all of them together creating a disk nearly 300,000 kilometers across, but in most places less than 10 meters thick. If you could shrink Saturn's rings to the size of a football field while maintaining their proportions, they would be thinner than tissue paper. The spacecraft flew through the ring plane, passing through the gap between the F ring and the G ring, a carefully calculated trajectory that avoided the densest concentrations of particles while giving the instruments the best possible view. The images that came back showed structure on structure, detail on detail. There were gaps cleared by small moons. There were density waves, ripples propagating through the rings like waves on a pond. There were spokes, dark radial markings that appeared and disappeared on timescales of hours, probably made of tiny dust particles levitated by electrical charges. But Voyager's mission at Saturn wasn't just about the rings. The close encounter with Titan revealed a moon shrouded in a thick orange atmosphere, thicker than Earth's, made primarily of nitrogen with traces of methane and other organic compounds. Voyager couldn't see through the smog to Titan's surface, but the measurements it made suggested this was a deeply strange and interesting world, cold enough that water ice was as hard as rock and methane could exist as liquid, possibly forming lakes or seas. That possibility would eventually lead to another mission, Cassini, which would confirm decades later that Titan does indeed have lakes of liquid methane and ethane, the only other body in the solar system besides Earth with stable liquid on its surface. Saturn itself showed its own character. Like Jupiter, it's a gas giant with no solid surface, but its atmosphere is calmer, its weather less violent, its bands of clouds more subtle. The planet's rapid rotation, just over 10.5 hours per day, creates a noticeable bulge at its equator. Its low density, lower than water, means Saturn would float if you could find an ocean big enough to hold it. Voyager 2 arrived at Saturn 9 months after Voyager 1 in August of 1981, taking a different trajectory that brought it even closer to the rings, passing just 41,000 kilometers from the planet's cloud tops. Its images confirmed and extended what Voyager 1 had found, filling in gaps, answering some questions while raising others. As Voyager 1 departed Saturn, it faced a choice encoded in its trajectory. It could continue onward to Uranus and Neptune, following the same path Voyager 2 would take, or it could use Saturn's gravity to deflect upward, out of the plane where the planets orbit, taking it close to Titan for better measurements but ending its tour of the planets. The mission planners chose Titan. Voyager 1 bent away from the ecliptic plane, beginning a journey that would take it above the solar system's disk, heading toward interstellar space by a more direct route. Voyager 2, now alone, continued onward. The next planet awaited, a world so distant that even at the spacecraft's tremendous speed, it would take more than 4 years to arrive, a world unlike any other, spinning on its side, wrapped in mystery. Let's pause here and contemplate what had to happen for these missions to be possible. The alignment of the outer planets, the configuration that made the Grand Tour feasible, doesn't come around often. Every 175 years, Jupiter, Saturn, Uranus and Neptune arrange themselves in such a way that a spacecraft can visit all four, using each planet's gravity to boost speed and change direction, cutting decades off the travel time that would otherwise be required. The last time this alignment occurred was in the late 1700s, when the United States was just forming, when electricity was a curiosity investigated by people like Benjamin Franklin, when the fastest way to travel was by horse or sailing ship. Before that, the alignment had happened in the early 1600s, when Galileo was first turning his telescope toward the heavens, when no one knew what planets really were, when the solar system's architecture was still being debated and mapped. The next alignment won't come until the mid-2150s. By then, we might have other means of exploring the outer solar system. We might have faster spacecraft, better propulsion systems, even crewed missions to the outer planets. Or we might not. Technology doesn't always progress in straight lines. Societies change, priorities shift, funding comes and goes. The fact that we seized the opportunity when it arrived in the 1970s, that we built these spacecraft and sent them on their journey, represents not just technical capability but also vision, commitment, a willingness to invest in knowledge that would take years to acquire. The Grand Tour concept had been proposed in the late 1960s by a graduate student named Gary Flandreau, who was working at NASA's Jet Propulsion Laboratory during a summer job. He was calculating trajectories, running numbers on the big computers of the day, trying to figure out the most efficient paths to the outer planets, and he noticed the alignment. He saw that if you launched in the late 70s, you could visit all four giant planets with a single spacecraft, using gravity assists at each one. The discovery excited the space community. Here was a chance to explore the outer solar system comprehensively, to visit worlds that had never been seen up close, to answer questions about the solar system's formation and evolution. But there were doubts. Could a spacecraft survive for the decade or more that the full Grand Tour would require? Could it remain functional in the intense radiation environment of Jupiter? In the cold darkness beyond Saturn? Could the communication systems work over distances so vast that radio signals would take hours to cross them? Could engineers on Earth diagnose and fix problems with a spacecraft billions of kilometres away? The answers, as it turned out, were yes, but it required extraordinary engineering. Every component had to be robust, redundant when possible, designed to operate for far longer than typical spacecraft lifetimes. The computers, primitive by today's standards, had to be reliable enough to execute complex sequences without constant oversight. The power systems had to function for decades. The attitude control systems, which kept the spacecraft oriented properly, had to work flawlessly, because even a small pointing error over interplanetary distances would mean missing targets by thousands of kilometres. And the mission planners had to think ahead, anticipating problems that might arise years in the future, programming responses into the spacecraft's computer memory, building flexibility into the mission design so that if something went wrong, there would be alternatives, workarounds, ways to salvage at least some of the science, even if not everything went according to plan. The Grand Tour was ambitious, some said too ambitious, but the people working on Voyager believed it was possible. They believed that with careful engineering, thorough testing, and perhaps a bit of luck, these two small spacecraft could survive the journey, could return the data, could expand humanity's knowledge of the outer solar system in ways that no Earth-based telescope ever could. And they were right. The mission succeeded beyond anyone's most optimistic hopes, but we're getting ahead of ourselves. Before Voyager 2 could complete the Grand Tour, it had to reach the next planet, a world that would challenge everything the spacecraft's designers thought they knew about planetary atmospheres and magnetic fields. 4.5 years after leaving Saturn, after a journey through the cold darkness of the outer solar system, Voyager 2 approached Uranus. The planet appeared first as a greenish disk, featureless and strange, growing slowly in the spacecraft's cameras. This was uncharted territory in the most literal sense. No spacecraft had ever been here before. No one knew quite what to expect. Uranus orbits the Sun at a distance of nearly 3 billion kilometres, about 19 times farther from the Sun than Earth. At that distance, sunlight is dim, a faint glow rather than the brilliant illumination we experience on Earth. The planet takes 84 Earth years to complete one orbit, meaning its seasonal cycle spans decades. One season on Uranus lasts 21 years. Imagine a winter that long, or a summer. But the most distinctive thing about Uranus, the feature that makes it unique among the planets, is its tilt. Most planets spin roughly upright, with their rotation axes nearly perpendicular to the plane of their orbits. Earth tilts about 23 degrees, which gives us our seasons. Jupiter and Saturn tilt only a few degrees, but Uranus tilts 98 degrees. It spins on its side, rolling around the Sun like a barrel rather than spinning like a top. This means that during parts of its orbit, one pole points almost directly at the Sun, while the other points away into darkness, giving Uranus the most extreme seasons of any planet. Why does Uranus spin this way? Does Uranus spin? The leading theory suggests that billions of years ago, during the solar system's violent youth, Uranus was struck by a massive object, perhaps an Earth-sized planet or several large bodies, impacts powerful enough to knock the planet onto its side. The collision would have been catastrophic, releasing enough energy to melt the planet's interior, yet Uranus survived, reformed, and has been spinning sideways ever since. Voyager 2 made its closest approach to Uranus on January 24th, 1986, passing within 81,500 kilometres of the planet's cloud tops. The encounter lasted only a few hours at close range, but in that time, Voyager gathered data that revolutionised our understanding of this distant world. The planet's atmosphere turned out to be mostly hydrogen and helium, like Jupiter and Saturn, but with significantly more methane. It's the methane that gives Uranus its blue-green colour. Methane absorbs red light and reflects blue and green, tinting the entire planet. Beneath the atmosphere, scientists believe there's a layer of water, methane, and ammonia ices under high pressure, surrounding a rocky core. Uranus isn't a true gas giant like Jupiter. It's an ice giant, a somewhat smaller type of planet where ices dominate the interior. The planet's magnetic field surprised everyone. Most planets generate their magnetic fields through dynamo action in their cores, with the magnetic axis roughly aligned with the rotation axis. But Uranus's magnetic field is tilted 60 degrees from its rotation axis and offset from the planet's centre. The field doesn't emerge from the poles but from mid-latitudes, creating an extremely lopsided magnetic environment. As Uranus rotates, its magnetic field wobbles crazily, creating one of the strangest magnetospheres in the solar system. Voyager discovered 10 new moons around Uranus, adding to the 5 large moons that were already known. The new moons were small, dark, orbiting close to the planet, shepherding the rings. Yes, Uranus has rings, though they're nothing like Saturn's bright bands. Uranus's rings are narrow, dark, made of material that reflects very little light. They look almost like stripes of charcoal circling the planet, probably made of organic compounds baked by radiation into a dark, carbon-rich substance. The 5 large moons, Miranda, Ariel, Umbriel, Titania, and Oberon, each showed unique geology. Miranda in particular astonished scientists. It's a small moon, only about 470 kilometres in diameter. Yet its surface showed a chaotic mix of terrains, old cratered regions next to young grooved areas, massive cliffs up to 15 kilometres high. The moon looked as if it had been smashed apart and reassembled, though the actual explanation is probably more subtle, involving tidal heating and geological activity billions of years ago. The encounter with Uranus was brief. Voyager 2 had only one chance to get everything right, to point its instruments correctly, to take the planned images, to make the scheduled measurements. There was no opportunity for a second pass, no way to go back if something was missed. The spacecraft's trajectory carried it past Uranus and onward, already aimed at its final planetary target, Neptune, still more than 3 years away. Behind Voyager, Uranus resumed its slow roll around the Sun, its secrets only partially revealed, its sideways spin a reminder that planets, like people, sometimes bear the scars of ancient violence. Yet they endure, they continue, they spin on through their long orbits, indifferent to whether anyone is watching. 3.5 years after leaving Uranus, on August 25, 1989, Voyager 2 reached Neptune, the last planet on its grand tour, the final world it would ever visit. By now, the spacecraft had travelled for 12 years, had survived radiation, cold, and the slow degradation of its components. Some instruments had failed, some had degraded. But the core system still functioned, still responded to commands radioed from Earth across 4.5 billion kilometres of space, commands that took 4 hours to arrive. Neptune orbits the Sun at an average distance of 4.5 billion kilometres, 30 times farther from the Sun than Earth. At that distance, the Sun appears not as a disk but as an extremely bright star, providing only about 1/900th the illumination Earth receives. Yet Neptune is not a cold, dead world. It's the most dynamic planet in the outer solar system, with winds howling at over 2,000 kilometres per hour, the fastest in the entire solar system, and weather systems that rival Jupiter's in violence if not in size. The planet's blue colour is deeper, richer than Uranus's pale cyan. Like Uranus, Neptune contains abundant methane, which absorbs red light, but there's something else in Neptune's atmosphere. Some additional absorber that makes the blue more intense. Scientists still aren't entirely sure what it is. As Voyager approached, Neptune's disk resolved into detail. The planet showed bands of clouds, bright cirrus-like streaks of methane ice forming high in the atmosphere, and there was a storm, a dark oval reminiscent of Jupiter's great red spot but smaller and darker, a region of downwelling atmospheric gas that appeared black against Neptune's blue clouds. The team called it the Great Dark Spot. It was about the size of Earth, a hurricane that had probably been spinning for decades or centuries, driven by energy from Neptune's interior. Neptune radiates more than twice as much heat into space as it receives from the Sun. Deep in the planet's interior, something is generating warmth, probably heat left over from the planet's formation, slowly leaking outward, driving the atmospheric circulation that creates Neptune's extreme weather. Without this internal heat source, Neptune would be a frozen, static world. Instead, it's one of the most meteorologically active planets known. The closest approach took Voyager 2 within 5,000 kilometers of Neptune's cloud tops, the closest the spacecraft would come to any planet during its entire mission. At that distance, the instruments could resolve details as small as a few kilometers across. The images showed cloud features changing on timescales of hours, atmospheric motions faster and more dramatic than anything seen on Uranus, a planet that was, by comparison, serene and quiet. Neptune's magnetic field, like Uranus's, all proved to be tilted and offset from the planet's centre, suggesting that both ice giants generate their magnetic fields in unusual ways, perhaps in shallow layers of electrically conductive fluids, rather than deep in their cores. The magnetic axis is tilted 47 degrees from the rotation axis, creating another wildly complex magnetosphere. Then there was Triton, Neptune's largest moon, and the primary target of Voyager's post-encounter phase. Triton orbits Neptune backwards, in the opposite direction to the planet's rotation, suggesting it wasn't formed alongside Neptune but was captured later, pulled in by the planet's gravity after forming elsewhere in the outer solar system. Capturing a moon that large requires precise conditions, and Triton likely paid a price. Tidal forces from Neptune probably melted its interior, drove geological activity, reshaped its surface. Voyager. 2 passed within 39,000 kilometers of Triton, close enough to see detail, to map the surface, to measure the temperature. What it found was one of the coldest objects in the solar system, with surface temperatures around 38 Kelvin, only 38 degrees above absolute zero. At those temperatures, nitrogen freezes solid. Triton's surface is primarily frozen nitrogen, with patches of methane and carbon dioxide ice. Despite the cold, Triton is geologically active. Voyager's images showed geysers, plumes of nitrogen gas erupting from beneath the surface, carrying dark organic material high into the thin atmosphere before the material fell back, creating dark streaks across the ice. Active geology on a world that far from the sun was unexpected, wonderful, a reminder that planets and moons continue to surprise us, continue to reveal processes and phenomena we hadn't anticipated. After the encounter with Neptune and Triton, Voyager 2's planetary mission was complete. There were no more worlds to visit, no more targets in the outer solar system. The spacecraft's trajectory carried it southward, below the plane of the planet's orbits, heading out of the solar system at an angle that would never bring it close to another planet. Both Voyagers were now in the final phase of their missions, no longer exploring planets, but studying the solar system's boundaries. The region where the sun's influence fades and interstellar space begins. But before we follow them there's a moment we need to revisit, a photograph taken during the mission, an image that changed how many people thought about Earth, about home, about our place in the vastness of space. On February 14th, 1990, Voyager 1 was more than 6 billion kilometers from Earth, beyond Neptune's orbit, heading toward interstellar space. Its planetary mission had been complete for years. The spacecraft's cameras, no longer needed for scientific observations, had been turned off to conserve power and reduce wear on the scan platform that aimed them. But Carl Sagan, one of the original champions of the Voyager missions, had an idea. He wanted Voyager to turn around, to look back at the solar system one last time, to take a family portrait of the planets from the outside looking in. The idea met resistance. The manoeuvre would risk the scan platform, which had already experienced problems during the mission. The images wouldn't have scientific value. There were valid reasons to leave the cameras off, to not attempt something that was purely about perspective, about philosophy rather than data. But Sagan persisted, and eventually NASA agreed. On Valentine's Day, 1990, Voyager 1 turned its cameras back toward the inner solar system and took a series of photographs capturing Jupiter, Saturn, Uranus, Neptune, Earth, and Venus from its distant vantage point. The images were transmitted back to Earth, and among them was one that would become iconic. Earth, seen from 6 billion kilometers away, a pale blue dot suspended in a sunbeam. The Earth in that image occupies less than a single pixel. It's tiny, insignificant against the vastness of space, a point of light that could be mistaken for a piece of dust or a camera artifact. The bright band crossing the image is scattered light from the sun, an artifact of the camera optics, but it makes the Earth look even more fragile, a mote of dust suspended in a sunbeam. Sagan wrote about this image in a way that captures its significance better than any technical description could. He noted that Earth, in that photograph, is home. It's everyone you know, everyone you've ever heard of, every human being who has ever lived. All of our joys and sufferings, all the human dramas, all the civilizations and empires, all the explorers and inventors, all the artists and poets, all the lovers and parents and children existed on that pale blue dot, a single pixel in the cosmic ocean. He reflected on the folly of human pretensions, of our imagined self-importance, of the delusion that we have some privileged position in the universe. The photograph, he suggested, underscores our responsibility to deal more kindly with one another, to preserve and cherish that pale blue dot, the only home we've ever known. Because there's nowhere else, at least in the near future, to which our species could migrate. Like it or not, for the moment, Earth is where we make our stand. The pale blue dot photograph reminds us of context. It puts our planet in perspective, shows us how small we are in the grand scheme of things, but it also shows us something precious, that all the beauty, all the complexity, all the life and love and meaning we know exists on that tiny point of light. We are small, yes, but we are also remarkable. We evolved on that dot. We built civilizations there. We created art and music and literature. We figured out the laws of physics, decoded the structure of DNA, sent spacecraft to explore the solar system. All of that happened on that pale blue dot. And from our vantage point here on Earth, other stars might have their own pale blue dots circling them, other worlds where life has evolved, where intelligent species might have arisen, where beings unlike us might be looking up at their sky, wondering if they're alone. We don't know. We haven't found them yet. But the possibility exists, and that possibility adds another layer to the photograph's meaning. When Voyager 1 took that picture, it demonstrated something essential about exploration. That sometimes the most important discoveries are not about what's out there, but about seeing ourselves more clearly. The spacecraft was sent to explore Jupiter, Saturn, and beyond, to gather data about other worlds. But in turning around to photograph Earth, it gave us something equally valuable, a portrait of ourselves from the outside, a chance to see our world as it really is, a single, fragile, beautiful point of light in the overwhelming darkness of space. After taking the family portrait, Voyager 1's cameras were turned off permanently. They had done their work. The images had been captured. The spacecraft continued onward, carrying its memories of the solar system, moving farther from the pale blue dot with every second, heading towards stars it will reach tens of thousands of years from now, long after everyone who built it, everyone who operated it, everyone who saw its images has been gone for generations beyond counting. Yet that photograph remains, a moment frozen in time, a perspective preserved, a reminder of where we came from and, perhaps, of what we should remember as we think about where we're going. Behind every space mission, there are people, human beings with hopes and dreams, with visions of what might be discovered and what it might mean. For the Voyager missions, one of the most influential voices was Carl Sagan, a scientist who believed that space exploration was not just about gathering data, but about expanding human perspective, about inspiring wonder, about helping people understand their place in the cosmos. Sagan had been involved with NASA missions since the early days of the space program. He worked on Mariner missions to Venus and Mars, contributed to the Apollo program, helped select landing sites for the Viking landers that touched down on Mars in the mid-1970s. But Voyager gave him a platform to reach beyond the scientific community, to communicate directly with the public about what these missions meant and why they mattered. He was instrumental in creating the Golden Record, chairing the committee that selected its contents, wrestling with the impossible task of representing humanity in sounds and images. The process forced him and his colleagues to think deeply about what defines us as a species, what we'd want aliens to know about us if they ever found the record. They could have chosen to represent human achievement, technology, military might. Instead, they chose to emphasize our diversity, our creativity, our relationships, our connection to the natural world. Sagan understood something that not all scientists grasp, that the facts alone, while important, are not enough to capture the human imagination. You need story, you need emotion, you need to connect the discoveries to people's lives, to help them see why a moon's volcanoes or a planet's rings matter, what these distant worlds tell us about our own world, our own existence. He had a gift for language, for finding the phrase that captures an idea perfectly. When he described the Earth as a pale blue dot suspended in a sunbeam, he wasn't just describing a photograph. He was offering a meditation on human significance and insignificance, on our responsibility to each other, on the preciousness of the only home we know. The image became iconic partly because of his words, because he gave it meaning beyond the pixels, beyond the technical achievement of taking a photograph from 6 billion kilometers away. Sagan also understood the importance of accessibility. Science, he believed, should not be the exclusive province of specialists. It belongs to everyone. The discoveries made by missions like Voyager are part of our collective heritage as a species, and everyone should have the opportunity to understand them, to be excited by them, to see in them what he saw. Evidence of a universe far stranger and more beautiful than most people imagine. He wasn't naive. He knew that scientific knowledge doesn't automatically make people wiser or kinder. He understood that technology can be used for harm as well as good, that the same curiosity that drives exploration can drive exploitation. But he believed deeply that understanding the universe, seeing Earth in cosmic context, recognizing our connection to the larger cosmos, makes it harder to sustain the divisions and conflicts that have plagued human history. When Voyager flew past Jupiter and discovered active volcanoes on Io, Sagan saw not just a geological phenomenon, but a demonstration that the universe is full of ongoing processes, that worlds we thought would be dead and frozen are instead active, evolving, changing. When Voyager found hints of an ocean beneath Europa's ice, he recognized the profound implication that life might exist elsewhere in our own solar system, that we might not be alone even in our cosmic neighborhood. He lived to see both Voyagers complete their primary missions, saw the images from Neptune and Triton, saw the pale blue dot photograph taken at his urging, but he died in 1996 before the spacecraft crossed into interstellar space, before they detected the heliopause, before they entered the space between stars that he had written about with such eloquence. Yet his influence continues. The Voyager missions are part of his legacy, as is the Golden Record, as is the pale blue dot photograph and the meditation it inspired. He taught a generation of scientists that it's not enough to discover. You must also explain, communicate, inspire. You must help people see the wonder in what you found. Help them understand why these distant worlds and abstract concepts matter. And he reminded us that we are, all of us, made of star stuff, atoms forged in the hearts of ancient suns, organised by billions of years of evolution into beings capable of contemplating the cosmos, capable of building spacecraft and sending them to explore, capable of understanding, at least partially, the universe that gave us birth. That's the dream he carried, and it's the dream that Voyager embodies, that we are part of something larger, that the universe is knowable, that exploration reveals not just facts but meaning, not just data but wonder. Let's turn our attention to something more technical but equally remarkable: how these spacecraft stay alive. After more than 45 years in space, after travelling billions of kilometres, after operating in temperatures that would freeze any conventional battery solid, Voyager 1 and 2 are still transmitting data back to Earth. That's only possible because of the power systems they carry. Radioisotope thermoelectric generators that have been producing electricity steadily since the spacecraft launched. Solar panels, the power source for most spacecraft in the inner solar system, become useless beyond Jupiter. The sunlight is simply too weak. At Jupiter's distance, the sun provides only 4% as much light as it does at Earth. At Saturn, it's 1%. At Neptune, it's 1/9 of 1%. You'd need solar panels the size of a football field to generate meaningful power, and even then, the panels would be so massive that launching the spacecraft would be impractical. So Voyager uses a different technology, RTGs, radioisotope thermoelectric generators. Each spacecraft carries 3 of them, mounted on a boom extending from the main body to keep their heat and radiation away from the sensitive instruments. Inside each RTG is plutonium-238, a radioactive isotope that decays steadily, producing heat. That heat is converted into electricity using thermocouples, devices that generate voltage when one side is hot and the other is cold. The plutonium-238 used in Voyager's RTGs has a half-life of about 88 years, meaning that every 88 years, half of the remaining plutonium decays. When Voyager launched, each spacecraft's RTGs produced about 470 watts of electrical power, enough to run a few light bulbs. By now, decades later, the output has declined to about 250 watts and continues to drop slowly. But that's still enough to power the spacecraft's essential systems: the computers, the radio transmitter, a few remaining instruments, the heaters that keep certain components from freezing. The engineers who designed Voyager knew the power would decline. They built in flexibility, ways to shut down non-essential systems, to manage power carefully, to extend the mission as long as possible. Over the years, instruments have been turned off one by one as power became scarcer. The cameras were shut down after Neptune because they were no longer needed and consumed power better used elsewhere. The ultraviolet spectrometer was turned off. The scan platform that moved instruments was powered down. What remains are the instruments studying the space environment: the magnetometer, measuring magnetic fields; the plasma detector, tasting charged particles; the cosmic ray detector; and the plasma wave instrument, which listens to radio emissions from the sun and from interstellar space. These instruments continue to return data that no other spacecraft can provide, because no other spacecraft has travelled so far, has entered the region where Voyager now operates. The RTGs will continue producing power for years to come, possibly into the 2030s or beyond, depending on how carefully power is managed and which systems remain operational. Eventually, though, the power will drop below the threshold needed to maintain contact with Earth. One by one, systems will fail or be shut down. The transmitter will go silent. Commands sent from Earth will receive no response. And Voyager will continue its journey in silence, still functioning perhaps, but no longer able to speak to us, no longer part of our ongoing conversation, lost to us though still existing, still moving through the galaxy. But that's years in the future. For now, the RTGs hum quietly, converting decay heat to electricity, powering the instruments, enabling the spacecraft to send back data at a rate of 160 bits per second, so slow by modern standards that downloading a single photograph would take hours, yet adequate for the measurements being made, for the science being done. There's something poetic about the power source. Plutonium-238 is an artificial isotope created in nuclear reactors, produced by humans through our understanding of nuclear physics. We made it, refined it, shaped it into pellets, sealed it inside the RTGs, and sent it into space. And now, decades later, those atoms are still decaying, still producing heat, still enabling the spacecraft to function. In a very real sense, the mission is powered by nuclear decay, by the slow transformation of plutonium into uranium, a process that will continue long after the spacecraft has fallen silent, long after everyone who built it has died, long after perhaps even our civilization has changed beyond recognition. The spacecraft themselves will outlast their power sources by millions of years. Even after they go silent, even after every component has frozen solid, they'll continue their trajectories, drifting through the galaxy, encountering other stars in the distant future, carrying the golden record, carrying evidence of a species that once lived on a small planet orbiting a yellow star, a species curious enough to build these machines and send them out into the endless dark. After completing their tours of the planets, both Voyager spacecraft continued outward, moving deeper into the outer solar system, into regions where the sun's influence begins to weaken, where the solar wind, that stream of charged particles emanating from the sun, starts to encounter resistance from the surrounding interstellar medium. The sun creates around itself a bubble called the Heliosphere, inflated by the solar wind, a region where the sun's magnetic field and particles dominate. This bubble extends far beyond the planets, billions of kilometers into space, separating the solar environment from the interstellar environment. But it has an edge, a boundary called the heliopause, where the solar wind's pressure balances the pressure of interstellar gas and magnetic fields. Crossing that boundary, entering interstellar space, was always a goal for Voyager. But for years no one knew exactly where the heliopause was located. Estimates range from 10 to 20 billion kilometers from the sun. The spacecraft were heading in the right direction, moving fast enough to reach the boundary within their expected operational lifetime, but whether they'd survive long enough to make measurements on the other side remained uncertain. Voyager 1 crossed the heliopause on August 25, 2012, at a distance of about 18 billion kilometers from the sun, roughly 122 times Earth's distance from the sun. The crossing wasn't dramatic. There was no wall, no sudden change. Instead, over a period of weeks, the spacecraft's instruments detected gradual shifts in the environment, a drop in the intensity of solar particles, an increase in cosmic rays from outside the solar system, a change in the direction of magnetic fields. The mission team analysed the data carefully before announcing that Voyager 1 had entered interstellar space, making it the first human-made object to do so. It was a historic milestone, the end of one phase of the mission and the beginning of another. After 35 years of travel, Voyager 1 had left the sun's protective bubble and entered the space between stars, carrying humanity's message into a realm no previous spacecraft had reached. Voyager 2 crossed the heliopause about 6 years later, in November 2018, at a slightly different location and with different measurements because its trajectory took it through a different part of the boundary. Together, the two spacecraft have given us our first direct measurements of interstellar space, confirming theories, revealing surprises, showing that the boundary is not uniform but varies in structure and properties depending on where you cross it. Interstellar space is not empty. It's filled with gas, extremely tenuous, only a few atoms per cubic centimetre compared to trillions of atoms per cubic centimetre in Earth's atmosphere, but still present, still detectable. There's also dust, grains of silicates and carbon compounds no larger than smoke particles, drifting between the stars, sometimes clumping into clouds that eventually collapse to form new stars and planets. And there are magnetic fields, weak but pervasive, created by the motion of charged particles through space, influenced by stellar winds from nearby stars, shaped by the Milky Way's galactic magnetic field. These fields guide cosmic rays, high-energy particles accelerated by supernova explosions and other violent events, particles that travel at nearly the speed of light and bombard everything in their path. Voyager's instruments measure all of this: the density of particles, the strength of magnetic fields, the intensity of cosmic rays, the presence of radio emissions from various sources. The data is sparse, limited by the spacecraft's aging instruments and declining power, but it's irreplaceable. No other spacecraft operates in interstellar space. No other measurements like these exist. The crossing of the heliopause doesn't mean Voyager has left the solar system. It's left the sun's bubble of influence, yes, but it's still bound by the sun's gravity, still moving through a region dominated by the sun's mass. The solar system, defined gravitationally, extends much farther, out to the Oort cloud, a vast sphere of comets orbiting the sun at distances of tens of thousands of astronomical units. Voyager won't reach the Oort cloud for thousands of years. It won't leave the solar system in that sense for tens of thousands of years, but in terms of the local environment, in terms of the particles and fields that surround the spacecraft, Voyager is no longer in the solar system's active zone. It's in interstellar space, sampling the galactic environment, measuring the medium between stars. That transition, from Heliosphere to interstellar space, from our star's domain to the galaxy's domain, represents a threshold crossed, a boundary traversed, a journey continued into a realm that will never end for these spacecraft, for they will drift through the galaxy for millions or billions of years, silent eventually, but enduring. Witnesses to a species that once wondered what lay beyond its small blue world. To understand what Voyager crossed when it entered interstellar space, we need to think about how the sun shapes space around it. The sun is not a static object, but an active, dynamic star, constantly emitting particles and radiation, constantly exerting influence on its surroundings. From the sun's upper atmosphere, from the corona, a steady stream of particles flows outward, electrons, protons. Some heavier ions, all moving at hundreds of kilometers per second, pushed away from the sun by the heat and pressure of the solar atmosphere. This is the solar wind, and it carries with it the sun's magnetic field, threading through space, connecting the sun to everything in the heliosphere. Near Earth, the solar wind moves at about 400 kilometers per second and contains about 5 particles per cubic centimetre. That's incredibly tenuous by any earthly standard, but it's enough to create effects. The solar wind shapes Earth's magnetosphere, compressing it on the sunward side, stretching it into a long tail on the night side. When solar wind conditions change, when the sun produces a coronal mass ejection or a solar flare, the enhanced particles and magnetic fields can interact with Earth's magnetic field, producing auroras, disrupting satellites, even affecting power grids. As you move farther from the sun, the solar wind spreads out, its density decreasing, but its speed often increasing because there's less material ahead to slow it down. By the time you reach the outer planets, the solar wind is faster but thinner, still present, still detectable, still carrying the sun's influence outward, but it cannot continue forever. Eventually it encounters resistance. The interstellar medium, the gas and dust between stars, has its own pressure, its own magnetic field. Where these two regions meet, where the pressure of the solar wind balances the pressure of the interstellar medium, you find the heliopause. The boundary Voyager crossed. The structure is more complex than a simple boundary, though. Before reaching the heliopause, the solar wind encounters a shock wave called the termination shock, where it slows down abruptly as it starts to pile up against the interstellar medium. Voyager 1 crossed the termination shock in December 2004, at a distance of about 94 astronomical units from the Sun. Voyager 2 crossed it in August 2007, at 84 astronomical units. Between the termination shock and the heliopause lies a region called the heliosheath, where the solar wind has slowed but is still present, flowing around the sides of the heliosphere before being deflected backward by interstellar pressure. The spacecraft spent years travelling through the heliosheath, measuring its properties, tracking how conditions change with distance, documenting the sun's influence even in this far region. Beyond the heliopause, in interstellar space, the solar wind is largely absent, replaced by interstellar gas flowing past the solar system, flowing past the sun at about 23 kilometers per second, a gentle breeze by cosmic standards, but still significant. This interstellar wind comes from a specific direction, from the general direction of the star Altair, shaped by the sun's motion through the galaxy and by local variations in the interstellar medium's density and velocity. What Voyager found at the heliopause was that the boundary is not smooth. It's dynamic, rippling, responding to variations in solar wind pressure, bulging outward when the sun is active and solar wind pressure is high, contracting inward during quieter periods. The spacecraft crossed the boundary, then detected temporary excursions back into the heliosheath, then crossed again, suggesting the boundary had moved past it, then moved back, then moved past again. This variability makes sense when you think about it. The sun's activity varies on an 11-year cycle, with periods of high activity featuring many sunspots and frequent solar storms, alternating with quieter periods when sunspots are scarce and solar output is steadier. These variations propagate outward through the solar wind, taking years to reach the outer heliosphere, but eventually affecting the heliopause's location and structure. The heliosphere itself is not spherical, it's more like a teardrop, compressed on the side facing the direction of the sun's motion through the galaxy, stretched out into a long tail on the opposite side. Voyager 1, heading north and outward, crossed the heliopause where it's relatively close to the sun. Voyager 2, heading south and outward, crossed at a different location, where the heliopause may be shaped differently by local variations in interstellar conditions. Together, the measurements from both spacecraft are giving us our first three-dimensional view of the heliosphere's structure, revealing how our solar system interacts with the broader galactic environment, showing us the edge of our star's influence, the place where our home star's breath finally fades into the whisper of the galaxy. It's a boundary defined not by solid material, but by pressure and plasma, by magnetic fields and particle flows, by the slow dance of gas and energy in the near vacuum of space. And now, for the first time, we have measurements from both sides of that boundary, data that will inform our understanding of not just our solar system, but of how all stars interact with their surroundings, how stellar winds shape their local environments, how the galaxy and its stars coexist in an ongoing exchange of matter and energy. At Voyager 1's current distance, radio signals take more than 22.5 hours to travel from the spacecraft to Earth. For Voyager 2, it's slightly less, about 19 hours, but still a staggering span of time. When mission controllers send a command, they must wait nearly a full day to know if it worked. Every action requires patience. Every decision must be made carefully, because mistakes cannot be corrected quickly. The radio signal itself is extraordinarily weak by the time it reaches Earth. Voyager's transmitter produces only about 23 watts of power, comparable to a refrigerator light bulb. That signal spreads out as it travels, diluting into a sphere that grows larger with every kilometre crossed. By the time it reaches Earth, the signal is about 1 billion times weaker than when it left the spacecraft. Receiving such a faint signal requires enormous antennas. The Voyager missions communicate through NASA's Deep Space Network, a collection of 3 facilities placed around the Earth so that at least one is always in view of the spacecraft as Earth rotates. The antennas are massive, 70 meters in diameter for the largest dishes, structures that weigh hundreds of tons, that can be pointed with incredible precision to track spacecraft across billions of kilometers. Even with these enormous antennas, the received signal is barely above the background noise of the universe. Radio waves come from everywhere, from Earth's atmosphere, from the sun, from the galaxy, from distant radio sources like quasars and pulsars. Voyager's signal must be extracted from this cacophony, separated from the noise, decoded and converted into the measurements that the spacecraft's instruments are making. The data rate is painfully slow. Voyager transmits at 160 bits per second, a rate so slow that sending a single modern photograph would take days. In the early parts of the mission, when the spacecraft were closer, data rates were higher, allowing thousands of images to be transmitted from Jupiter and Saturn. But as distance increased, the rate had to be reduced to maintain reliability. Now, 40 plus years into the mission, the spacecraft send back only scientific measurements, numerical data describing magnetic fields, particle counts, plasma properties. No more images, no more detailed readings from multiple instruments, just the essential measurements from the instruments still operating. The people who receive this data, who command the spacecraft, who keep them functioning, work at NASA's Jet Propulsion Laboratory in Pasadena, California. The Voyager mission operations team has shrunk over the decades from hundreds of people during the planetary encounters to just a handful now. Specialists who understand the spacecraft intimately, who know its quirks and limitations, who can diagnose problems based on subtle changes in telemetry, who can write code for 45-year-old computers and upload it successfully across interstellar distances. They're doing work that has never been done before. Operating spacecraft this old, this far away, requires improvisation, careful planning, and a deep knowledge of systems that were designed by people who are now retired or deceased, using technologies that are obsolete on Earth but still functional in space. The spacecraft's computers have less memory than a basic calculator. Their software is written in assembly language, low-level code that speaks almost directly to the hardware. Making changes requires understanding not just what you want the spacecraft to do, but how to implement it within the severe constraints of available memory and processing power. And yet the mission continues. Commands are sent. The spacecraft respond. Data flows back across the vast distance, carrying information about regions of space no one has ever measured before, answering questions about the boundary between the solar system and interstellar space, confirming some theories, refuting others, always revealing more complexity than models predicted. There's something profound about this exchange of signals. On Earth, people think about what to command, write code, transmit it through enormous antennas. The signal races outward at light speed, the fastest anything can travel, yet still takes nearly a day to arrive. The spacecraft receives the command, executes it, begins making measurements, packages the data, transmits it back. Another day for the signal to return. And then, finally, people on Earth see the results. Learn what the spacecraft has found, analyse the data, think about what to ask next. It's a conversation conducted at the speed of light across a distance so vast that even light requires more than a day to bridge it. It's a dialogue between humanity and its most distant ambassadors, a connection that persists despite the growing gulf, despite the weakening signals, despite the slow degradation of systems that were never designed to work this long. One day, the conversation will end. The power will drop below critical levels, or a key component will fail, or the spacecraft will simply become unresponsive. Commands will be sent, but no reply will come back. The mission will be over, at least in terms of active communication. But until that day arrives, the exchange continues, data flowing homeward, commands flowing outward, humans and machines collaborating across the longest distance over which we have ever maintained contact with our own technology. Behind every great technological achievement are people, often working quietly, solving problems few others know exist, keeping complex systems functioning through expertise, dedication, and sometimes sheer stubborn refusal to let failure win. The Voyager missions have been blessed with such people, engineers and scientists who have devoted years, in some cases decades, to keeping these spacecraft alive and productive. Consider Suzanne Dodd, who has been the Voyager project manager since 2010, though her connection to the mission goes back further. She has overseen the spacecraft through some of their most critical transitions, the entry into interstellar space, and the careful power management as the RTGs decline, the difficult decisions about which instruments to keep operating and which to shut down. Under her leadership, the team has extended the mission far beyond what anyone thought possible, squeezing more science from aging systems, finding creative solutions to problems that have no precedent. Or Ed Stone, the mission's project scientist since before launch, a man who has spent more than 45 years interpreting Voyager's data, explaining its significance, guiding the scientific program through countless changes and challenges. He's been the public face of Voyager for much of its lifetime, the person who stood before cameras after every planetary encounter, after every major discovery, translating the findings into terms the public could understand, conveying the excitement without overhyping the results. His steady presence, his clear explanations, his obvious love for the mission have made him synonymous with Voyager in many people's minds. There are others, less publicly visible but equally essential. The navigation team that tracks the spacecraft's positions with incredible precision, that plans trajectory corrections when needed, that ensures commands will reach the spacecraft at the right time. The engineers who maintain the Deep Space Network's antennas, keeping those enormous dishes functioning, performing upgrades, solving problems with equipment that must receive signals weaker than a whisper. The programmers who write code for ancient computers, working within constraints that would seem absurd to modern software developers, yet producing reliable, efficient programs that keep the spacecraft operating. And there were the people who came before, who designed Voyager in the 1970s, who tested it, who launched it, who navigated it through the first planetary encounters. Many of them have retired, some have died, but their work endures in the spacecraft still travelling, still functioning, still doing what they were designed to do 45 years ago. The mission has required constant adaptation. Problems arise that no one anticipated. The scan platform on Voyager 2 jammed during the Saturn encounter, a terrifying moment that threatened to ruin the rest of the mission. The team diagnosed the problem remotely, developed a workaround, and eventually regained full functionality. One of the thrusters on Voyager 1 started showing signs of degradation after decades of use. Engineers switched to a backup set of thrusters that hadn't been fired in 37 years, and they worked perfectly. Power management has become increasingly critical. As the RTGs produce less electricity, the team has had to turn off instruments one by one, prioritizing which measurements matter most, which can be sacrificed. Every watt is precious. Every system that uses power is scrutinized. The team has even developed ways to warm critical components using heat from other systems, reducing the need for electrical heaters, saving a few watts that can be used elsewhere. Communication protocols have been refined. The spacecraft now transmit data in longer blocks, which is more efficient but requires more power to be stored up before transmission. The ground antennas have been upgraded over the years, becoming more sensitive, able to receive weaker signals than was possible when the mission began. These improvements have brought additional years of operations, pushing the end of the mission further into the future. The team members speak about the spacecraft with genuine affection. They describe Voyager 1 and 2 almost as elderly relatives, systems that have quirks, that need careful attention, that surprise you sometimes with their resilience, but that also require constant monitoring to catch problems before they become critical. It's not anthropomorphizing in a naive way. It's recognizing the human effort embedded in these machines, the care with which they were built, the ongoing care required to keep them functioning. And there's a poignancy to the work. Everyone involved knows the mission will end. The spacecraft will eventually fall silent. The exact timing is uncertain, but it's coming, maybe in the late 2020s or early 2030s, maybe a few years earlier or later depending on power and system health. When that day arrives, the people working on Voyager will have to say goodbye to spacecraft they've kept alive for years or decades, machines they've communicated with daily, whose signals they've waited for, whose data they've interpreted and analysed. It will be a loss, felt personally by the team members, even though they know it's inevitable, even though they've done everything possible to extend the mission as long as it could be extended. And yet there will also be satisfaction, knowing they succeeded, knowing they pushed the boundaries of what's possible, knowing that Voyager's legacy is secure, that the data it returned has transformed our understanding of the solar system and the space beyond, that the spacecraft will continue their journey long after contact is lost, carrying humanity's message towards stars they'll reach thousands of centuries from now. When the Golden Record was created, the team encoded greetings in 55 languages, ranging from ancient tongues to modern ones spoken by billions. One of those languages was Sumerian, an ancient language spoken in Mesopotamia thousands of years ago, a language that hasn't been spoken natively since the 2nd century BCE, preserved only in cuneiform texts and through the efforts of scholars who have learned to read it. The Sumerian greeting on the Golden Record says, quote 5, a simple sentiment, offered by a language dead for 2,000 years, now travelling through space. Carried by a spacecraft that will outlast every language currently spoken on Earth. Languages change, they evolve, merge, split, die out, get replaced. Of the roughly 7,000 languages spoken on Earth today, linguists estimate that half will be gone by the end of this century, replaced by dominant languages like English, Mandarin, Spanish, or absorbed as communities shift, as globalization spreads, as younger generations adopt different tongues than their grandparents spoke. Over longer timescales, all current languages will change beyond recognition or vanish entirely. English in the year 3000 will be as different from modern English as modern English is from Old English, perhaps more so. 1,000 years from now, a recording of our speech might be incomprehensible to our descendants, might require translation, might be studied by linguists the way we study ancient Greek or Sanskrit. 10,000 years from now, the linguistic landscape of Earth will be completely transformed. The languages on the Golden Record, even those with billions of speakers today, may be extinct, preserved only in recordings and texts, remembered by scholars and AI systems but spoken by no one. Yet the record will still exist, still carrying those greetings, still preserving sounds and words from languages that no longer have speakers. This is part of what makes the Golden Record so poignant. It's not just a message to aliens. It's a time capsule, a preservation of humanity at a particular moment, capturing languages, music, sounds, images that will change or vanish as Earth continues its long turning. The record is, in a very real sense, immortal in a way that human languages and cultures are not. It's sealed in aluminum, encased in gold, protected from erosion and decay, travelling through the near vacuum of space where nothing will corrode it, nothing will wear it down. Billions of years from now, when the sun has become a red giant and consumed the inner planets, the Golden Record will still exist, unchanged, perfect, carrying its frozen moment of humanity toward encounters that may never come. The record contains music by Blind Willie Johnson, a blues singer from Texas who died in poverty in 1945. It contains a night chant from the Navajo people, a culture that has survived conquest and suppression, but whose language is now endangered. It contains greetings in languages like Akkadian and Aramaic, languages with ancient roots and uncertain futures. Every piece of content on the record carries this same bittersweet quality. It's preserved perfectly, but the contexts that gave it meaning are ephemeral. Think about that for a moment. The record will outlast not just individuals, but species, languages, possibly civilizations. If humans colonize other worlds, if we spread through the galaxy, the cultures and languages of Earth will diversify beyond anything we can imagine now. We'll split into variants that can't understand each other. We'll develop new forms of communication we haven't conceived. And through all that change, Voyager will still be carrying its sample of late 20th century Earth, a tiny snapshot of one moment in one place. Or consider the alternative. If humanity doesn't survive, if we succumb to climate change or nuclear war or some other catastrophe, the golden record becomes even more important. It becomes the last voice of a species, the only evidence that we existed, that we created art and music, that we developed language and science, that we reached out into the cosmos hoping to make contact, to share ourselves with whatever might be out there. The linguists who selected the greetings chose languages partly for diversity, wanting to represent different language families, different parts of the world. But they also chose some languages for their historical significance or their number of speakers. They couldn't include all 7,000 languages spoken at the time. They had to make choices, and those choices have consequences. The languages on the record are remembered. The thousands not included are not, at least not in this particular memorial to humanity. As the years pass, as decades become centuries, as centuries become millennia, the golden record will become increasingly precious, not because of what it might tell aliens, but because of what it preserves about us. About who we were in 1977, what we valued, what we hoped for. It's a message in a bottle, yes, but it's also a gravestone, a monument, a memorial to a species that existed, that tried to understand its universe, that reached as far as it could into the great dark beyond its small world. And somewhere in that sentiment lies a gentle sadness, but also a strange comfort. We won't last forever. Nothing does. But we were here. We made these things. We sent them out. And they'll remain, long after we're gone, carrying proof that we existed, that we mattered, at least to ourselves. Voyager 1, moving at about 17 kilometers per second relative to the Sun, is heading toward a small dim star in the constellation Camelopardalis called Gliese 445. At its current speed, Voyager 1 will pass within about 1.5 light years of that star in approximately 40,000 years. 40,000 years. That's longer than recorded human history. 40,000 years ago, humans were hunter-gatherers, scattered across Africa, Europe and Asia, living in small groups, using stone tools, following herds, painting images on cave walls. Writing didn't exist. Cities didn't exist. Agriculture hadn't been invented. The great civilizations of Mesopotamia, Egypt, China, all the empires and kingdoms and nations that have risen and fallen throughout recorded history, all of that was still in the future, unimaginable to the people living then. And yet that vast span of time, that entire arc of human development from Stone Age to Space Age, is less than the time Voyager 1 will take to reach the vicinity of another star. It puts the scale of interstellar distances into perspective in a way that numbers sometimes don't. Even our fastest spacecraft, even Voyager moving at 17 kilometers per second, tens of thousands of kilometers per hour, barely crawls across the gulf between stars. Gliese 445 is a red dwarf, a small cool star with perhaps 10% the Sun's mass, much dimmer, much less luminous. If Voyager could transmit images back to us when it passes by, which it won't, because its systems will have failed thousands of years before, those images would show a star unlike our Sun, redder, dimmer, probably with a family of planets very different from ours if it has planets at all. But Voyager won't slow down. It won't stop. It will pass through that star system at the same speed it's travelling now, taking only a few years to traverse the system before continuing on into the darkness beyond. And then it will be heading toward another star, and another, on a journey that has no destination, no end point, no finish line. Voyager 2, meanwhile, is heading toward a different star, Ross 248, another red dwarf. It will pass within about 1.5 light years of Ross 248 in about 42,000 years. After that, it will continue towards Sirius, the brightest star in our night sky, passing within about 1.5 light years of the Sirius system in about 300,000 years. 300,000 years. Our species, Homo sapiens, is perhaps 300,000 years old. We evolved around the time Voyager 2 will be reaching Sirius, assuming no external force alters its trajectory. Think about the entire span of human existence, every generation, every life, every moment of joy and suffering and discovery and forgetting, and that's how long it will take Voyager 2 to reach one of our closest bright stars. And even after these encounters, if we can call them that, the spacecraft will continue. They'll pass other stars, dozens of them over millions of years, hundreds over tens of millions of years, thousands over hundreds of millions of years. They'll orbit the Milky Way's centre along with the Sun and all the other stars in our galactic neighbourhood, taking about 230 million years to complete one orbit, moving through the galaxy's spiral arms, through regions of star formation and empty spaces, through clouds of dust and across voids. They'll encounter the galaxy's hazards, high-velocity stars that might pass close enough to perturb their trajectories, clouds of gas thick enough to exert drag, magnetic fields strong enough to influence their path through space. These interactions will be rare, but over millions of years they'll accumulate. The spacecraft's orbits will change, slowly, unpredictably. Where they'll be in 1 billion years is impossible to predict with any accuracy. The cumulative effects of countless small perturbations will make their paths chaotic in the mathematical sense, sensitive to initial conditions in ways that make long-term prediction meaningless. But they'll still be travelling. That much is certain. They have no way to slow down, no way to stop. They're in orbit around the Milky Way centre, just as the Sun is, just as every star in the galaxy is. They'll participate in the galaxy's slow rotation, its gradual evolution as stars are born and die, as the galaxy's structure shifts, as time passes on scales we can barely conceive. 5 billion years from now, when the Sun exhausts its hydrogen fuel and begins to swell into a red giant, when the inner planets are consumed and Earth is either engulfed or scorched into a lifeless cinder, Voyager will still be out there, unchanged, still travelling, still carrying its golden record. The spacecraft will have seen nothing, experienced nothing, because they're machines without consciousness, without awareness, but they'll endure, silent witnesses to the galaxy's long turning, to the slow dance of stars and dust and dark matter that makes up the Milky Way's substance. And that's strangely beautiful, isn't it? That these small things we built will persist long after we're gone, will travel farther than we ever will carry some echo of humanity into a future so distant that the Sun itself will have died, that Earth will no longer exist in any recognisable form. We made something that will outlast our world, our star, possibly our entire civilization. That's an achievement worth contemplating, worth feeling proud of, even as we recognise how small we are, how brief our moment in cosmic history. Space is not empty, but it is very, very close to empty. In interstellar space, where Voyager now travels, there are about 0.1 atoms per cubic centimetre. For comparison, Earth's atmosphere at sea level contains about 25 billion atoms per cubic centimetre. The difference is almost incomprehensible. Interstellar space is about 1 billion times less dense than the air you're breathing right now. If you could stand in interstellar space, if you could somehow survive the vacuum and radiation and cold, you would encounter essentially nothing. Hours might pass before a single atom happened to strike you. Days might pass before you encountered a speck of dust. You would see stars, of course, brilliant points of light scattered across the darkness, but they would be distant, far away, their light taking years or decades or centuries to reach you. There would be no sense of motion, no feeling of speed, because there's nothing nearby to move past, no reference points except the slow change in star positions, so gradual that you'd need weeks or months to notice it. This is the environment Voyager travels through now. The solar system, with its bustling activity, its planets and moons and asteroids, its solar wind and magnetic fields, is behind them. Ahead lies only more emptiness, interrupted occasionally by slightly denser regions where interstellar clouds drift, by slightly less dense regions where old supernovae have blown bubbles in the interstellar medium, by the occasional passage near a star's heliosphere where conditions might resemble those the spacecraft left behind. The spacecraft feels none of this. It has no sensors for loneliness, no programming for appreciation or fear. It simply continues, executing its commands, making measurements when possible, transmitting data back toward Earth as long as power allows. But there's something almost melancholy in thinking about these machines, alone in the dark, so far from home, still trying to do their jobs, still faithful to their programming, still reaching back across the growing distance to speak to us. They'll be alone for an extraordinarily long time. The nearest star to the Sun is Proxima Centauri, about 4.2 light-years away. At Voyager's speed, reaching Proxima Centauri would take about 75,000 years, and Voyager isn't headed toward Proxima. The stars Voyager will eventually pass are all farther away, requiring tens of thousands of years to approach, and even then, the spacecraft won't enter their systems, won't orbit them. Won't do more than pass nearby before moving on. Between those distant stellar encounters, there will be nothing but emptiness. Millennia upon millennia of travelling through the dark, through regions where stars are visible but distant, where no planets exist to see, where nothing happens except the slow, steady movement of the spacecraft through the thin gas of the interstellar medium. It's peaceful, in a way. There are no dangers here, no immediate threats, no asteroids to collide with, no intense radiation belts like those around Jupiter, no gravitational fields to capture the spacecraft or fling them off course. Just the slow, eternal drift through the near vacuum, the temperature gradually equalizing to the cosmic background radiation's 3 Kelvin, just a few degrees above absolute zero. As the last heat from the RTGs dissipates, and the spacecraft becomes as cold as the space around it. Humans have always filled silences with meaning, interpreted emptiness through stories and metaphors. We can't help but project onto Voyager, can't help but imagine what it might feel to be so alone, so far from anything, travelling toward nowhere in particular, no longer in contact with Earth, no longer receiving commands or acknowledgements, just existing, moving, enduring. But perhaps that projection is itself meaningful. Perhaps the fact that we care about these machines, that we think about them, that we find poetry in their isolation, says something important about us, about our need for connection, our discomfort with loneliness, our desire to matter, to be remembered, to send something of ourselves into the future even knowing we won't be there to see it arrive. Voyager's journey through the silence between stars is our journey too, in a metaphorical sense. We live on a small world, isolated in space, separated from other stars by distances we can barely cross even with our fastest machines. We send out signals, build spacecraft, create messages, hoping something might respond, might acknowledge us, might confirm that we're not alone in the universe, and mostly we're met with silence. Not the hostile silence of active rejection, but the neutral silence of vast distance, of physical separation, of a universe where light itself is slow compared to the spaces between things. It's a gentle silence, really, not unfriendly, just empty, just waiting, just existing without judgment or malice. And in that silence Voyager travels on, carrying its small cargo of human sounds and images, proof that at least once, in one small corner of the universe, beings existed who wondered what else was out there, who reached out despite the odds, who sent their voices into the dark hoping someone, something, might someday hear. The silence doesn't diminish that gesture. In some ways it makes it more profound, more poignant, more human. Let's return once more to the golden record, to the cargo Voyager carries, to the message we sent to whoever or whatever might find these spacecraft in the distant future. The record is 12 inches in diameter, weighs about 1/3 of a pound, is made of gold-plated copper for longevity. The aluminum cover has diagrams explaining how to play it, using universal concepts like the transition of hydrogen atoms to convey information about duration and frequency. Inside that record is a condensed portrait of Earth and humanity. 115 images encoded as audio signals that can be decoded into pictures, photographs of mathematical equations explaining concepts like prime numbers and planetary orbits, pictures of DNA's double helix structure showing the molecular basis of life, images of human anatomy, both internal and external, photographs of people from different cultures, a mother nursing a baby, old men smiling, children playing, people in various traditional dress. There are images of animals, insects and fish, birds and mammals, a variety of life forms showing the diversity of Earth's biosphere, pictures of landscapes, mountains and deserts, forests and oceans, the Grand Canyon and a sunset, images of human achievements, ancient monuments like the pyramids and the Taj Mahal, modern cities with their skylines of glass and steel, a supermarket full of food, a highway full of cars. The record attempts to show both what we are and what we aspire to be. Not just our technology, but our art. Not just our knowledge, but our emotions. Not just our achievements, but our relationships, our connections to each other and to the natural world we come from. The 90 minutes of music are perhaps the most revealing part of the record. Music is universal among human cultures. Every society produces it. Every culture has songs, rhythms, melodies, instruments. But musical traditions vary enormously. What sounds beautiful in one culture might sound strange or discordant in another. The committee selecting music for the Golden Record faced an impossible task: represent the breadth of human musical expression in an hour and a half. They chose Bach's Brandenburg Concerto and Beethoven's Fifth Symphony, masterpieces of Western classical music, compositions that demonstrate complex harmonic structures and emotional depth. They chose Stravinsky's The Rite of Spring, a piece that challenged musical conventions when it premiered and continues to sound modern decades later. But they also chose music from dozens of other traditions: a Peruvian wedding song, a night chant from the Navajo people, a Japanese shakuhachi piece, throat singing from Tuva, a piece for gamelan from Java, a Pygmy girl's initiation song from Zaire. They included Chuck Berry's Johnny B. Goode, rock and roll representing a uniquely 20th century American musical form. They included Blind Willie Johnson's, quote, "nine a haunting slide guitar blues that sounds like wordless lamentation, like loneliness given musical form. They included Louis Armstrong playing, quote, 10, the genius of jazz improvisation captured in a few minutes. Each piece was chosen not just for its own merit, but for what it revealed about human creativity, about our ability to organize sound into patterns that move us, that express emotions beyond words, that connect us across cultures and generations. An alien listening to the Golden Record wouldn't understand the cultural contexts, wouldn't know what jazz or blues or classical music means to humans, but they might recognize that these sounds are intentional, structured, meant to convey something beyond mere information. The spoken greetings in 55 languages show our diversity of communication. The sounds of earth, thunder and wind and ocean waves and animal calls show our planet's sonic environment, the soundscape we evolved in, the audio world that shaped our species. The greetings from UN Secretary-General Kurt Waldheim and President Jimmy Carter provide a political and temporal context, anchoring the record to a specific moment in human history, though by the time anyone might find it, those names will mean nothing. Those political structures will have changed beyond recognition or ceased to exist. What the record cannot convey is the complexity of human experience. It can't show suffering or injustice, can't represent war or poverty or disease, can't capture the full range of human emotion from deepest despair to highest joy. It shows a curated version of humanity, emphasizing our creativity and knowledge, downplaying our capacity for cruelty and destruction. That's not dishonest exactly, but it is selective. Yet perhaps that selectivity is appropriate. The record is meant as a greeting, an introduction, a hand extended in friendship. You don't introduce yourself by listing your worst qualities. You show your best face, your achievements and hopes, while acknowledging implicitly that you're complex, that there's more to you than can be shown in a brief presentation. The golden record is ultimately an act of hope. Hope that someone will find it. Hope that they'll be able to decode it. Hope that they'll be curious about the strange organic beings who made it. Hope that the universe contains other intelligence, other consciousness, other beings who wonder about their place in the cosmos just as we do. And even if no one ever finds it, even if the record drifts through space forever unheard and unseen, its creation was worthwhile, because it forced us to think about who we are, what defines us, what we'd want to share about ourselves with hypothetical aliens, and in doing so, perhaps we learned something about ourselves, saw ourselves more clearly, understood ourselves a little better. There will come a day, probably sometime in the late 2020s or early 2030s, when the power from Voyager's RTGs drops below the threshold needed to operate the transmitter. On that day, the spacecraft will receive a command from Earth, and for the first time in its long mission, it won't be able to respond. The mission controllers will wait for a signal that doesn't come. They'll send the command again and again, and eventually they'll have to accept that Voyager can no longer hear them, or if it can hear, it cannot reply. The exact sequence of the end is impossible to predict. Power decline is gradual but not perfectly linear. Component failures could come suddenly or might never come. The mission team has developed contingency plans for various scenarios, but ultimately, the end will unfold in its own way, determined by engineering decisions made 45 years ago and by the accumulated effects of decades in the harsh environment of space. Before power becomes insufficient to transmit, the team will likely have shut down all remaining instruments to conserve energy for communication. The spacecraft will become mute scientifically, no longer measuring particle counts or magnetic fields, no longer gathering data about the interstellar medium, but still able to transmit housekeeping data, still able to receive and acknowledge commands. Then, as power declines further, even that will become impossible. The transmitter requires power. The spacecraft systems require power. Below a certain threshold, there's not enough electricity to maintain communications. The spacecraft might still be alive internally, its computer still running, its systems still functioning on minimal power, but it will have become invisible to us, unable to signal its status, unable to receive new instructions. The mission team will have to decide when to send the final commands, what those commands should be, how to say goodbye to a spacecraft that has exceeded every expectation, that has revolutionized our understanding of the outer solar system, that has become, in some ways, an icon of human achievement and aspiration. Perhaps they'll command the spacecraft to shut down non-essential systems, to enter a minimal power state, to preserve functionality as long as possible. Perhaps they'll send a message acknowledging the end, thanking the spacecraft, though of course it cannot understand, cannot feel gratitude or satisfaction or closure. These gestures would be for the humans involved, a way to mark the ending, to create ceremony around loss. Or perhaps they'll simply send the last routine command, upload the last software patch, request the last data dump, and then wait for a signal that never comes, and that will be the end, undramatic, without fanfare. Just the absence where communication used to be. For the people working on Voyager, this ending has always been approaching. They've known for years that it's coming, have watched the power budget decline, have made the hard decisions about which instruments to shut down and when. Yet knowing the end is coming doesn't make it easier when it arrives. These are people who have devoted significant portions of their careers, in some cases their entire careers, to these missions. They've formed relationships with the spacecraft, not in any mystical sense, but in the way anyone forms relationships with things they work with daily, things they understand intimately, things that respond to their commands and provide feedback and data. When Voyager falls silent, it will mark the end of an era. No other spacecraft operates so far from Earth. No other mission has lasted so long or returned so much transformative data. Future missions may eventually surpass Voyager's distance, may make new discoveries in the outer solar system or interstellar space, but Voyager will always be first, will always hold that distinction, will always represent a time when we reached farther than we ever had before, when we sent machines to places we'd only imagined, when we asked profound questions about the universe and found answers that surprised and delighted us. After the end of communications, Voyager will continue its journey, of course. The spacecraft won't stop just because we can't hear from them anymore. They'll keep travelling at their steady 17 kilometres per second, will continue moving away from the Sun, will pass through the interstellar medium, will eventually approach other stars. The mission continues in that sense even after contact is lost. The spacecraft remain our ambassadors to the galaxy, whether we can communicate with them or not. But for us, here on Earth, the end of communication is the end of the mission. We'll have the data, the images, the measurements, all preserved and available for analysis. We'll have the scientific papers, the books, the documentaries. We'll have the memory of what Voyager achieved, what it showed us, what it meant. But we won't have the ongoing connection, the daily exchange of signals, the reassurance that our emissaries are still out there, still functioning, still speaking to us across the vast dark. And so, when that day comes, when the last signal is received and no new signals follow, the people who have kept Voyager alive will gather, probably to mark the moment, to acknowledge the loss, to celebrate the achievement, to say goodbye to spacecraft that have been their companions for years or decades. That have given meaning to their work, that have connected them to something larger than themselves, to a mission that touched the cosmos and brought back wonders. When all the systems have failed, when the power is gone, when the spacecraft have fallen silent, what remains? Metal and plastic, electronics and wiring, mechanisms that once moved but now are frozen, computers that once processed but now are inert. Voyager will become an artifact, a relic. A piece of late 20th century technology drifting through the galaxy, gradually cooling to match the temperature of the space around it. At 3 Kelvin, just a few degrees above absolute zero, the spacecraft will be as cold as space itself. At that temperature, materials behave differently than they do on Earth. Metals become more brittle, plastics freeze solid, lubrication solidifies, any remaining movement stops. The spacecraft become frozen in time, their final configuration preserved. Nothing changing anymore because change requires energy and there's no energy left. Yet they don't disappear, they don't decay. In the near vacuum of interstellar space, there's nothing to corrode metal, no oxygen to rust steel, no water to wear away surfaces, no biological processes to break down materials. The spacecraft will persist essentially unchanged for millions or billions of years, perhaps longer, limited only by occasional impacts with dust grains or atoms, tiny collisions that gradually erode surfaces, that sandblast the exterior on timescales measured in millions of years. The golden record, protected inside its aluminum case, will likely survive even longer. Gold doesn't tarnish or corrode. It remains stable under extreme conditions. The grooves pressed into the record, the information encoded there, should be readable essentially forever, assuming someone or something finds it and figures out how to decode it. So what endures is memory, information, a snapshot of humanity preserved in metal and gold and plastic. Not a complete portrait, as we've discussed, but a meaningful one, a genuine attempt to represent ourselves honestly, to share something of who we were and what we valued. But there's another sense in which Voyager endures, in the minds and hearts of the people who built it, who operated it, who analysed its data, who shared its discoveries with the world. The spacecraft shaped careers, inspired vocations, changed perspectives. Thousands of people were directly involved with the mission over its decades of operation. Millions more saw the images, learned about the discoveries, felt some shift in understanding or perspective, some expansion of wonder. Those effects propagate forward. A child who saw images of Jupiter's storms might have become fascinated with planetary science, might have pursued a career studying atmospheres or space missions, might have mentored students who went on to make their own discoveries. The ripples of inspiration spread outward, touching lives, shaping futures, influencing the trajectory of human knowledge in ways both obvious and subtle. Voyager demonstrated what's possible when we commit to exploration. When we invest in understanding rather than exploitation, when we reach beyond immediate needs to pursue questions that have no economic payoff, but enrich our understanding of existence. The mission showed that humanity can undertake long-term projects, can build things that last, can achieve goals that take decades to accomplish, that require sustained effort and commitment and vision. In a world often focused on short-term gains, on immediate results, on quick returns on investment, Voyager stands as a counterexample, a demonstration that some things worth doing take time, that some questions worth asking require patience, that some achievements require looking beyond quarterly profits or election cycles to consider what we want to accomplish as a species, as a civilization, as inheritors of a planet that gave us birth and a universe that invites exploration. The data Voyager returned will be studied for generations. Scientists are still analysing measurements from the planetary encounters, still finding new insights in images taken decades ago, still writing papers based on observations made when many current researchers were children or not yet born. The information doesn't expire, it remains valuable, usable, reference material against which new observations can be compared, baseline measurements that characterise how the solar system appeared at a specific moment in time, and the inspiration continues. Every year, new people discover Voyager, learn its story, feel that spark of wonder. Young students learn about the mission in science class. Artists create works inspired by the golden record. Musicians compose pieces based on the sounds Voyager carries. Writers tell stories imagining the spacecraft's fate, its eventual discovery, its role in connecting humanity to whatever else exists in the universe. This cultural impact, this ongoing presence in human consciousness, is as much Voyager's legacy as the scientific data. The mission has become mythology while still being fact, has entered the realm of stories we tell about ourselves, about what we're capable of, about our relationship with the cosmos. So when we ask what endures after Voyager falls silent, after the last signal fades, the answer is everything that matters. The physical spacecraft endure, yes, but more importantly, the knowledge endures, the inspiration endures, the proof that we can do hard things, that we can work together toward common goals, that we can look beyond ourselves and our immediate concerns to engage with the universe on its own vast terms. That's Voyager's real legacy, and it will persist as long as humans remember to look up, to wonder, to ask questions about what lies beyond the familiar, comfortable boundaries of home. There's a concept in astronomy called the light horizon, the maximum distance from which light could have reached us since the Big Bang, given the age of the universe and the speed of light. Beyond that horizon, we can see nothing, know nothing, because light from those regions hasn't had time to reach us yet. The observable universe has a boundary, not because there's nothing beyond it, but because we can't see beyond it, can't receive information from those distant regions. Voyager is nowhere near that boundary. The spacecraft are still within our galaxy, still in our cosmic neighbourhood, still in a region where we can, in principle, receive signals from them. But they're approaching a different kind of horizon, a limit defined not by cosmic expansion, but by practical considerations. Power, signal strength, the sensitivity of our receiving equipment. Already, Voyager's signals are extraordinarily faint. The transmitter produces 23 watts. By the time that signal reaches Earth, it's diluted to about a billionth of a watt. Our largest antennas can still detect that whisper, can still extract data from the noise, but not indefinitely. As power declines, as the spacecraft move farther away, as components age and fail, the signal will become weaker, harder to detect, until eventually it falls below our ability to receive it, and Voyager will pass beyond our communications horizon, still existing, still transmitting perhaps, but speaking to no one, heard by nothing. When that happens, Voyager will truly be beyond our furthest reach, beyond our ability to interact with, beyond our connection, except through memory and imagination. The spacecraft will become fully independent, autonomous not by design but by circumstance, no longer responding to our commands because they can no longer hear them, no longer reporting back because we can no longer hear them. This is, in some ways, the natural end of any mission of exploration. The explorer eventually goes beyond the range where messages can reach home, beyond the point where rescue or assistance is possible, into territory that is genuinely unknown and unknowable. Early seafarers experienced this when they sailed over the horizon, out of sight of land, into waters no one from their culture had navigated. Space exploration extends that experience to cosmic scale, but the principle is the same. You reach a point where you're on your own, where whatever happens next depends entirely on your preparation, your equipment, your luck. Voyager was prepared well. The spacecraft were built with redundancy, with robust systems, with the expectation that they'd need to operate autonomously for years at a time. The mission planners anticipated the communications delay, designed procedures that allowed the spacecraft to handle routine operations without constant oversight, built in the ability to detect and respond to certain problems automatically. All of that foresight has paid off, allowing the mission to continue far longer than minimum requirements demanded. But even the best preparation has limits. Eventually something fails that can't be compensated for. Eventually the power drops too low. Eventually the mission ends not with a dramatic failure, but with a gradual fading, like a voice becoming quieter and quieter, until you can't make out the words anymore, and then you can't hear anything, and then there's only silence, and the knowledge that someone was speaking, even though you can no longer hear them. Beyond that horizon, beyond our ability to see or hear or know, Voyager continues. The universe doesn't stop just because we've lost contact. The spacecraft still exist, still move through space, still carry their cargo of human artifacts, still represent humanity's gesture toward the cosmos. They've become, in that sense, independent of us. No longer tools we're using, but monuments we've erected, memorials we've sent, messages we've launched, hoping someone someday might find them and understand what they represent. And perhaps that's appropriate. Perhaps the final stage of any exploration is letting go, releasing control, accepting that what you've sent out into the unknown will continue without you, will have its own fate independent of your wishes or knowledge. We sent Voyager to explore, and it did. We sent it to report back, and it has. Now, as it passes beyond our reach, we have to accept that its journey continues without us, that it will go places we'll never know about, will experience conditions we'll never measure, will drift through the galaxy for time frames we can barely imagine, all without any connection to the beings who built it. There's something beautiful in that independence, in that separation. We give our creations to the universe and trust that they'll endure, that they'll carry forward something of our hopes and dreams, that they'll represent us well in our absence. Voyager has earned that trust. It's done everything we asked and more. Now, as it travels beyond our furthest light, beyond our ability to reach or guide it, we can feel confident that it carries the best of us into a future we won't see, toward destinations we can't name, on a journey that truly has become infinite. In more than 45 years of travel, across billions of kilometres, through the Heliosphere and beyond, Voyager has encountered mostly emptiness. That's not a criticism or a disappointment. That's simply the nature of space. The vast majority of the universe is vacuum, or near enough to vacuum that the distinction barely matters. Matter is rare. Planets and stars and galaxies are the exceptions, not the rule. emptiness is normal, but Voyager has shown us that emptiness isn't featureless. The near vacuum of space has structure, has properties, has phenomena worth studying. The solar wind, thin as it is, carries magnetic fields, transports particles, shapes the environment around every planet. The heliosheath, that region between the termination shock and the heliopause, has currents and pressures, regions where particles pile up or spread out, places where magnetic fields intensify or weaken. Even interstellar space, emptier than anything between the planets, has its own character. The local interstellar cloud that our solar system is moving through has a certain density, a certain temperature, a certain magnetic field strength. These properties vary from place to place. Interstellar space is not uniform. There are clouds and voids, walls and filaments, regions carved out by ancient supernova and regions where gas has accumulated, waiting perhaps to collapse someday into new stars. Voyager's measurements have given us our first direct samples of this environment. Before Voyager crossed the heliopause, we had only models and theories and indirect observations. Now we have data, actual measurements taken in situ, showing what interstellar space is really like, at least in our immediate galactic neighbourhood. What they've found is a medium that's dynamic, that changes, that responds to influences from nearby stars, from the motion of the solar system through it, from the galactic magnetic field threading through everything. The local interstellar cloud is moving past us at about 23 kilometers per second, a gentle drift by cosmic standards, but still significant, still measurable, still affecting how the heliosphere is shaped, where the heliopause is located, how solar particles interact with interstellar particles. Voyager has shown us that you can do meaningful science even in apparent emptiness, that there are questions worth asking about the interstellar medium, about the boundaries between stellar influences, about how the galaxy is structured on large scales. These questions don't have the immediate appeal of what does Jupiter look like up close, or are there volcanoes on Io? But they're equally important for understanding the universe, for mapping the cosmic environment, for learning how stars like our Sun fit into the larger galactic context. And there's a philosophical dimension to Voyager's journey through emptiness. It mirrors in some ways the human experience. We live in a vast universe where most of space is empty, where the distance between stars is so great that light itself takes years to cross them, where intelligent life, if it exists elsewhere, is likely separated from us by gulfs we may never bridge. We are, in a very real sense, alone in the emptiness, calling out, hoping for a response that may never come. Voyager's journey through the empty places reminds us that the journey itself has value, that exploration is worthwhile even when you don't find what you hope to find, that learning about emptiness is still learning, still valuable, still worth the effort. The spacecraft didn't find alien civilizations or hidden wonders in interstellar space. It found what was actually there, a thin gas, a magnetic field, some cosmic rays, the ordinary background of the galaxy. But in measuring that ordinariness and characterizing it carefully, Voyager has given us knowledge we didn't have before, has answered questions we needed answered, has shown us that even emptiness has its secrets, its lessons, its quiet contributions to our understanding of the cosmos. Part of it is narrative. Voyager's story has a shape, a progression, an arc that resembles stories we tell about human journeys, departure, adventure, discovery, transformation, and ultimately, a slow transition toward an ending that approaches but never quite arrives. We connect with that narrative structure. We see in Voyager's journey echoes of our own journeys, our own departures from home, our own explorations of unknown territory, our own gradual separation from the familiar as we move forward into whatever comes next. But I think there's something more fundamental happening too. Voyager represents us. Not just in the sense that it carries the golden record, though that's important, but in a deeper sense it embodies human qualities, curiosity, persistence, the desire to understand, the willingness to venture into the unknown despite uncertainty and risk. When we talk about Voyager, we're talking about ourselves, about what we're capable of when we work together, when we commit to long-term goals, when we look beyond immediate concerns to engage with the larger universe. The spacecraft are made of metal, yes, but they're also made of human ingenuity, human effort, human hope. Thousands of people contributed to their creation and operation. Engineers solved problems no one had encountered before. Scientists designed experiments to answer questions no one had been able to test. Technicians assembled components with extraordinary precision. Mission planners calculated trajectories years in advance. Managers coordinated efforts across institutions and decades. All of that human effort is embedded in Voyager, is carried by Voyager, is represented by Voyager. When we say the spacecraft are explorers, we're acknowledging that they do more than execute commands. They carry forward a human impulse to explore, to know, to reach beyond what's familiar. They act on our behalf in regions we cannot go, sending back information we could not otherwise obtain, expanding our collective knowledge in ways that benefit everyone. And in that sense, Voyager is us, projected into space, extended beyond the confines of our bodies and our world, given duration and mobility we don't have as biological beings, granted a kind of immortality through metal and electronics, through design robust enough to function for decades, through a journey that will continue long after every person currently alive has died. That's why we care about these spacecraft, why we celebrate their achievements. Why we'll feel genuine loss when they fall silent. They're not just tools. They're extensions of ourselves, representatives of our species, carriers of our dreams and aspirations. They've earned the right to be considered explorers, not because they made independent choices, they didn't, but because they faithfully executed the mission we gave them, represented us well in distant places, brought back knowledge that changed how we understand the solar system and our place in it. When future historians, if there are future historians, look back on the 20th and early 21st century, they'll note Voyager as a significant achievement. They'll recognise that in sending these spacecraft we demonstrated capabilities and values worth acknowledging. We showed that we could build things that last, that we could work together internationally, that we could pursue knowledge for its own sake, that we had the vision to think beyond our immediate needs and immediate generations. Voyager started as machines, as tools built for a specific purpose. But through their long journey, through their achievements and their endurance, through the meaning we've invested in them and the ways they've expanded our understanding, they've become something more, symbols of human aspiration, monuments to human curiosity, explorers who carry our story into a future we cannot see, towards stars we will never reach, on a journey that has truly become infinite. One of the most profound aspects of Voyager's mission is its finality. The spacecraft are not coming back. They were not designed to return. They cannot return. Their trajectories carry them away from the sun, away from Earth, away from everything familiar, on paths that will never loop back, never reverse, never bring them home. This was understood from the beginning. The mission was planned as a one-way journey, a deliberate choice to maximize exploration at the cost of recovery. Every human mission before Apollo 11 landed on the moon had been designed with return in mind. Astronauts went to space knowing they would come back. Spacecraft orbited Earth, gathered data, then re-entered the atmosphere or landed. Even the Apollo missions, as bold as they were round trips. The astronauts knew that if everything went according to plan, they would return home, would see their families again, would walk on Earth after walking on the moon. Voyager has no such plan. The spacecraft were designed to leave and keep leaving, to become permanent wanderers, to travel until systems fail and silence falls, and then to continue travelling anyway, unpowered, uncontrolled, but still moving, still drifting through the galaxy on trajectories that, barring extraordinarily unlikely collisions, will carry them forward essentially forever. There's something elegiac about that. something that touches on fundamental human anxieties about departure and loss, and the one-way nature of time. We can't go back. None of us can. Time moves forward only. The past recedes behind us, growing more distant, harder to access clearly, until eventually it's just memory, and then not even that. Just history. Just stories other people tell about times we weren't alive to experience. Voyager embodies that forward motion, that irreversible departure. Every second it moves about 17 kilometres farther from home. Every day, about 1.5 million kilometres. Every year, over 500 million kilometres. The numbers accumulate, the distance grows, and there's no reversing it, no changing course to come back, no possibility of return even if we wanted it, even if we built a faster spacecraft to catch up and retrieve Voyager. The energy required to stop the spacecraft and send them back would be as much as it took to launch them in the first place. We don't have that capability at their current distances. We likely never will. So Voyager's journey is forever, or as close to forever as anything can be. The spacecraft will continue until collisions or tidal forces or some other external factor disrupts them, which could take millions or billions of years. They will drift through the galaxy, orbiting the Milky Way's centre along with hundreds of billions of stars, participating in the slow waltz of galactic rotation that takes hundreds of millions of years to complete. By the time Voyager 1 completes one orbit around the galaxy, the Sun will have evolved into a red giant and then collapsed to a white dwarf. Earth will be gone. The inner solar system will be unrecognisable. Yet Voyager will still exist, still moving, still carrying the golden record, still bearing its message from a species that may no longer exist, from a world that may no longer be habitable, from a time now so distant that even the stars have changed their positions. This permanence is both humbling and exalting. We are temporary. Our lives span decades at most. Our civilizations last centuries or millennia. Our species has existed for perhaps 300,000 years, a blink in geological time, an instant in cosmic time. Everything we build eventually crumbles. Every monument erodes. Every record degrades. Even the continents shift, the mountains wear down, the oceans rise and fall. Nothing lasts, except Voyager, in the near vacuum of space, with no weather, no erosion, no biological decay. The spacecraft will persist essentially unchanged for time frames that dwarf human history, that exceed the lifetime of species, that rival geological epochs. We built something that will outlast us by factors of millions. That's an achievement worth contemplating, worth feeling awe about. But it's also melancholy. Voyager will never come home. We will never touch it again, never see it with our own eyes except in photographs taken decades ago, never retrieve it and place it in a museum, never bring it back to study and preserve. It's out there, beyond our reach, moving farther away every moment, and that distance will only increase, will only grow, until the spacecraft is so far away that even light takes years to cross the gap, and then decades, and then centuries. There's a finality to that separation, a completeness to the departure that mirrors the finality of death, of loss, of the permanent absences that define human experience. We understand that Voyager is not coming back, and in understanding that, we confront something essential about existence, that we have to let go, that we have to accept permanent separations, that we have to find meaning not in keeping things close, but in allowing them to go, in releasing them to their fates, in trusting that what we've sent out into the universe carries something worthwhile even if we never see it again, even if we never know what becomes of it. Voyager's forever journey is our journey too, in that metaphorical sense. We all move forward into time, leaving the past behind, unable to return, unable to redo or reclaim what's gone. We all face endings, farewells, permanent separations from people and places we love. And we all have to find a way to make peace with that, to accept it, to see beauty in it rather than only loss. Perhaps that's part of why Voyager resonates with people, why its story touches something deep. It's not just a space mission. It's a meditation on departure and permanence, on reaching toward what we cannot hold, on sending our best selves forward into an unknown future, hoping that something of what we were, something of what we valued, will persist, will endure, will carry forward the message that we were here. We wondered, we explored, we reached toward the stars with hope and curiosity, and though we are temporary, what we made has become, in its own way, eternal. At this very moment, as you're listening to these words, Voyager is transmitting. The spacecraft's radio transmitter is generating a signal, encoding data from its instruments, beaming that signal back toward Earth across more than 22 billion kilometers of space. The signal travels at the speed of light, the fastest anything can go, yet still takes more than 22 hours to arrive. Right now, engineers at the Deep Space Network are tracking Voyager, pointing enormous 70-meter antennas at the tiny moving point where the spacecraft is. Receiving that faint signal, extracting data from the noise, processing it, storing it, analyzing it. Scientists are examining measurements of magnetic fields, particle counts, plasma properties, looking for patterns, comparing current readings to past readings, building models of the interstellar environment. The spacecraft doesn't know any of this, of course. It has no awareness, no understanding of its own significance. It simply executes its programming, takes measurements, packages the data, transmits. But the fact that it's still doing this, still functioning after 45 years, still providing useful data, still communicating across distances that make interplanetary space look tiny by comparison, is itself remarkable, worthy of appreciation. Think about what's required for this communication to work. The spacecraft must maintain its orientation, must keep its antenna pointed toward Earth, even as Earth moves in its orbit and the spacecraft continues outward. This requires the attitude control system to function, to make small adjustments, to compensate for the slow drift that would otherwise turn the spacecraft away from Earth. The power system must provide enough electricity to run the transmitter, the computer, the instruments, the heaters that keep certain components warm enough to function. The RTGs must continue converting decay heat to electricity efficiently enough that there's power for all essential systems. The transmitter must generate a stable, coherent signal at precisely the right frequency so that Earth's receivers can detect it. The computer must process data from instruments, format it correctly, control the transmission timing. The instruments themselves must still be taking measurements, their sensors still sensitive enough to detect the faint signals they're designed to measure. All of this must work together, every component functioning, every system coordinated despite 4.5 decades in space, despite temperature extremes, despite radiation exposure, despite the accumulated effect of cosmic ray hits and micrometeorite impacts and simple wear on components never designed to last this long. That it does work, that Voyager continues to function, speaks to the quality of the engineering, the care taken in design and construction, the robustness built into every system. But it also speaks to luck, to the absence of the kinds of catastrophic failures that could have ended the mission years ago, to the fortunate reality that nothing essential has broken beyond the team's ability to work around it. This ongoing communication is Voyager's final gift to us, these last years or decades of data, these measurements from a region of space no other instrument can reach, this knowledge that we could not obtain any other way. The spacecraft could have gone silent years ago. Everyone would have celebrated what had already been achieved, would have considered the mission a complete success based on the planetary encounters alone. Instead, we get bonus years, extra time, additional discoveries, all because Voyager keeps going, keeps working, keeps speaking across the vast distance. And every day the mission continues is another day of humanity maintaining its most distant connection, another day of receiving signals from our furthest representative, another day of proof that we can build things that endure, that our reach extends beyond our planet, beyond our solar system, into the space between stars. That's meaningful. That matters. One day, perhaps soon, the communication will stop. We've talked about that ending, about what it will mean, about how it will feel. But today is not that day. Today, Voyager is still speaking. Today, we can still hear it. Today, the conversation continues, data flowing homeward, commands flowing outward when needed, the connection maintained despite the distance, despite the decades, despite every reason it should have failed by now. So let's appreciate this moment, this ongoing achievement, this demonstration of what's possible when people work together toward ambitious goals, when engineers build with care and foresight, when scientists design experiments that can return value for decades, when societies decide that exploration and knowledge are worth pursuing even when the practical benefits aren't immediate or obvious. Voyager is still speaking after all these years. It's still out there, still functioning, still sending back data, still representing humanity in the deepest reaches of space any human artifact has ever touched. And as long as that signal keeps arriving, as long as we can detect that whisper across the cosmic distance, we have a connection to something larger than ourselves, something that extends beyond our individual lives and our immediate concerns, something that links us to the universe itself, to the grand project of understanding where we are, what we're part of, and what it all means. That signal, faint as it is a triumph. Every day it continues is another day of success, another day of connection, another day of human achievement echoing through the galaxy. We should celebrate that. We should feel proud of that. And when the day comes that the signal finally stops, when Voyager falls silent and begins its long drift into the endless dark, we'll remember these years when it was still speaking, still reaching back to us, still maintaining the conversation across the greatest distance over which humanity has ever communicated with its own technology. Thank you for staying with me through this entire journey. All 2.5 hours of it. We've travelled together through 45 years of one of humanity's greatest achievements, from the launch pads at Cape Canaveral to the edge of interstellar space, from the volcanic fury of Io to the icy plains of Triton, from the complexity of designing a message for alien civilizations to the simplicity of machines that keep working, keep trying, keep speaking long after they had any right to still function. We've wandered from Jupiter's swirling storms to Saturn's delicate rings, from Uranus spinning on its side to Neptune's wild winds. From the pale blue dot photograph that showed us home from billions of kilometres away to the golden record that carries our voices toward encounters thousands of centuries hence. From the team members who keep Voyager alive with skill and dedication to the profound questions about exploration and permanence and what it means to send something of ourselves into the forever. We've contemplated the silence between stars, the empty places that aren't really empty, the boundaries where the sun's influence fades and the galaxy's presence grows. We've thought about languages that no longer have speakers yet still travel through space, about machines that became explorers, about journeys that never end because there's nowhere to end, nothing to stop the motion, no destination except the endless drift through time and space. The question we opened with, the implicit question threading through this entire exploration, was perhaps this. What does it mean that we built these spacecraft, that we sent them so far, that they continue still, speaking to us from the deepest reaches of human achievement? The answer, as honestly as I can give it, is this. It means we are a species that looks beyond itself, that asks questions about existence and the universe, that reaches toward understanding even when the reaching is hard, even when the answers are slow to come, even when the journey requires decades of patience and effort and care. It means we can work together to achieve things larger than any individual could accomplish. It means we value knowledge, wonder, exploration, the expansion of human awareness beyond the comfortable confines of our small blue world. It means we're willing to invest in long-term projects whose payoff might not arrive until after we're gone. whose benefits accrue to future generations rather than to ourselves immediately. If you enjoyed this slow drift through Voyager's story, through the planets it visited and the spaces it crossed and the people who made it possible, a like and subscribe would help others find these calm explorations of space and science and human achievement. I read your comments, I appreciate your thoughts, and I'm grateful for this community of people who find peace in these long, detailed, thoughtful journeys through topics that matter. To those who have been with me for many of these documentaries, thank you especially. Your continued presence means everything. Wherever you are in the world right now, in whatever time zone, under whatever sky, I hope your breathing has slowed. I hope